Without multiplying another function into a double integral, we could say that the area of a region is the integration of the differential area. So notice we're not asking for a function to be over the region. We're asking for the boundaries to define our double integral. This is very similar to how we were finding area in Calc 2 when we did it with one within one variable. We would look for our boundaries and we would transfer the information over. But what we can do in this case is this creates the ability for us to kind of um, use the differential element of area to create what we need. So let's look at an example. I think, right. I hope we can dimensionally see if we don't have any multiplying function in here, then dimensionally this has the same units as area. And so what we're doing is we're integrating over 1. And it's the region definitions then that work on giving us the area. So let's look at, we're going to have a region that's bounded by y equals x and y equals x squared. As you've heard me a lot in here, I will like to draw these out. And so y equals x is that great identity function. Y equals x and y equals x squared. And then y equals x squared is our parabola. Motions to the right now seem to be coming off very crooked on this tablet for me. Something about the orientation here. And so I'm going to, right now, if we look at when these equal, when x equals x squared, they only equal when x equals 1. And so this is the point 1 comma 1. And this is the point 0 comma 0. And we have a boundary that's x squared to y, and y equals x. And so if we want to find what's happening in here, we can integrate parallel to y to find this area. All right, if we want to find this area, we'll integrate parallel to y. So if we integrate parallel to y, we're going to start with y equals x squared. Right, that's our bottom, and as we come up, we hit y equals x. And then we're going to integrate, if we're left over moving in x, since we already got our function in, 0 to 1. And we did y first, then dx. So notice we had no containing function within this. All right, we just set our boundaries for our two parts of our integral, and we moved across them. And so our area is going to equal, we'll do our integration in y first. So that's going to be y evaluated from x squared to x. And when we do that evaluation, it's going to be x minus x squared dx, evaluated from 0 to 1, which is x squared over 2 minus x cubed over 3, evaluated from 0 to 1, or 1/2 minus 1/3, or 1/6. So we can use this technique of multiple integrals as a way of breaking apart our motion or boundaries, and we can extend how we can find area on a surface given the complexity of that area.